Hello, everyone. My name is Michele Mancioppi. I am head of product of Dash0, an observability company that does OpenTelemetry native observability. But today, I'm not going to talk about my product. I'm going to talk about how to do OpenTelemetry better for everybody by reducing the amount of toil to roll out your telemetry collection. Please raise your hands if you were in this session for the previous talk. Only a few of you, right? It's going to be a very different talk than what you have seen in the previous two sessions. This is going to be a very technical talk. We're going to go down deep into the rabbit hole of making some extreme automation for the current OpenTelemetry SDKs out there. Also, a word of warning, this talk is thick. It would take me roughly 1 hour to do it properly with all the steps, taking questions. So please keep your scanners peeled, because if you blink it, you miss it. Of course, if you miss it, feel free to get to me after the talk or at the Dash0 booth, and I will bring you through the steps. All right, let's get started. Why does this talk matter? Earlier today, Hazel gave a great talk with a lot of insights about how to foster a culture of observability, how to roll out observability in organizations. And one thing really stuck with me is the fact that you need to be honest with people about how much effort rolling out observability can be. And quite frankly, it can be a bunch. It's not always easy. You really want to get the best bang out of your buck. So today, we are going to look at one of the ways to get a lot of bang for your buck, and those are no-touch instrumentations. So let's start maybe a little slower. What is an instrumentation? Raise your hands if you have a working mental model of how telemetry is generated inside your applications. Wow, I love you folks. So just so that we're all on the same page, effectively, you have inside your application some code that at runtime collects telemetry. And most of the time, automatic instrumentation, like for tracing, is going to be some sort of wrappers. If we were in the year 2010, I would use the word aspect-oriented programming. Today, the kids would call it callbacks, right? So you have code that captures what is going on, generates telemetry out of it. And there is a spectrum of instrumentations. The most basic kind is the one that you add to your application as code by coding against the OpenTelemetry API. You get a tracer, you start a span, you add attributes, you close the span. You go and create an instrument for metrics, a counter, and then invoke the add method. That is instrumentation you own. That's manual. You did it. Then there is automatic instrumentation. That is instrumentation that somehow you add to your application at runtime. The application itself, your jar file, your Node.js code, does not contain the instrumentation, but at runtime you mix them together and telemetry is collected. This is, for example, the case of the OpenTelemetry Java agent, AWS Lambda layers, and so on. Pretty much most languages that run on a runtime in the OpenTelemetry SDKs have some way of doing automatic instrumentation. Node.js, Python, Java, .NET, you name it. And then you go one step further in reducing the coupling of instrumentation collection from your application. You don't want even to package the stuff together. You just want to make it so you make some instrumentation somewhere, some configuration, and then all your applications magically get instrumented. Examples of this are eBPF-based instrumentation, really cool stuff going on there. The focus of this talk, so taking existing OpenTelemetry instrumentations and making them feel like magic, where you don't need to do anything, it just works. And then native instrumentations in frameworks and libraries. For example, Quarkus, Spring, Micronaut, just in the Java ecosystem, have instrumentation built in that will collect data. So How does today look like to use automatic instrumentations into your containers? This is a very simple Docker file for a Java application, and there are effectively 3 steps that you care about. The first is adding the application. You add your jar file, your code is in the container. Then you add the OpenTelemetry Java agent. This carries the instrumentation. And then you make the JVM care. You tell the JVM at runtime, load the OpenTelemetry Java agent. And this is done by setting the Java_tool_options environment variable. There are equivalent environment variables for most runtimes out there. In Node.js is node_options. PHP-RC. .NET, for some reason, has 6 of them that you need to use in tandem to activate automatic instrumentation, and so on and so forth. So, what is the state of the art of no-touch instrumentations? I'm going to focus on eBPF and what I'm going to talk about today. First of all, I have great respect for the eBPF instrumentation. It's really cool stuff. It has some drawbacks for now in terms of security. You need to give significant permissions. I hope that those limitations can be lifted. I have questions about the viability of eBPF-based instrumentations in serverless, because I don't think AWS Lambda is going to give you access to the kernel under the Lambda runtime. But eBPF has a place and a role. For example, if you run your own data center or your virtual machines, that's actually pretty good technology. You should look into that. And then there is the LD preload approach that I'm going to talk about today, which is using existing automatic instrumentations and make them feel every bit as automated as what eBPF can be. There is one caveat. It does not work for languages that are compiled. So if your applications are Rust or Go, this is not going to help you look into eBPF. For all the other SDKs of OpenTelemetry, that will work. And also C++, I should mention. Also, C++ is compiled. All right, so already today, with the OpenTelemetry operator, you can do some no-touch instrumentation, or at least automatic, and that is done through configurations. You go, and in the pod specifications on Kubernetes, you add the right annotations that are saying to the OpenTelemetry operator to please add to this pod, for example, the .NET instrumentation with the flavor for libc. And in the scope of the talk, you will understand why I'm focusing on .NET. I promise you that. Now, how do we go from a situation where you need to tell the operator, please add that instrumentation in that flavor, to just saying the operator just does everything automatically? That is mixing LD preload in the mix. Let's have again a look at the way that we were adding the OpenTelemetry Java agent into our container. We did 2 steps. One, we added the instrumentation as a file. And second, we activated at runtime the instrumentation by adding the right environment variable. And as a matter of fact, this generally works also outside of Kubernetes. The moment that you add the instrumentation in a place that your .NET, your Java, your Node.js can see it, can open the right files, and you manipulate the process environment of your application just right, you have won. But raise your hands if I talk about process environment. Are we all on the same page? Good, thank you. Just so we're on the same page, you can pass configurations to your applications by setting the environment. This is what happens in Kubernetes when you do env and then, for example, value from, and then you mount a secret, or you mount a config map, or just hard code the value in the pod spec. And we have been doing that in Linux since before I was in kindergarten. All right, so how do we actually make this on Kubernetes, step by step? First, we get the files inside our pods. And first, we need to look at how is a pod created. What is the process? The process is you have some YAML in some shape or form somewhere, and then you tell, for example, via kubectl apply to the kube API server, please create me a pod like this. And then the kube API server obliges you and creates a pod. But what if we actually added files to the pod in flight? So you have, again, your pod YAML. It knows nothing of OpenTelemetry. And when you do kube apply, the kube API server asks an admission controller mutating webhook, which is a facility that, for example, today we use to inject certificates, to validate settings, sometimes even to scan images, to please modify my pod so that it has all it needs. And then your pod, mutated with the additions, is running. How does that look like in practice? If you cannot read this, I'm very sorry. It was supposed, I was not ready for the size of this room. The point is, it's very, very simple. It's a pod, it has one container, it has one image. Simple, doesn't get simpler. And if we put it through the mutation, for example, like the one of the Dash0 operator, which is similar to the OpenTelemetry operator, you have something a little more complicated. How much more complicated? What does it do? Well, all this additional YAML, what does it do? It does two things. First, it automatically delivers the instrumentation through an init container. So your pod starts, there is an additional container in it. It will copy the instrumentations in an empty dir volume, which is backed by file, disk, or memory. It's ephemeral volumes. It goes away when the pod dies. And then you activate it. And this is a different environment variable than what we have seen in the Java use case, and it's going to be the centerpiece of the talk, LD preload. Now, before we get into how LD preload actually works for the use case of observability, we need to talk a bit about dynamic linking. Please raise your hands if you coded C or C++. Wow, I wonder if I should give this talk at all. You folks know it already. For those that had not had that kind of fun, when you actually run an application on a Linux system, more often than not, your binary is not standalone. It's not complete. It needs more. Of course, it needs to talk to the kernel, for example, to open files, but in reality, there are libraries that are added to your application after you compile it at runtime. And this is called dynamic linking. For example, if you were around to have a great time with the Heartbleed bug, when it turned out that some SSL implementations were not great in terms of security, you must have been very, very happy that to update your applications, you just updated a dependency. You updated a package in your Linux distribution, and a non-vulnerable version of SSL was automatically used by your application. You didn't need to recompile. That's the whole reason, well, at least a large part of the reason, why Linux distributions exist in the first place. You have a bunch of dependencies, the core of the distribution, that is used by applications. So most of your applications are going to use whatever OpenSSL version you have in your distro. And they're all going to use the same libc. This one is going to be important. This applies, the concept of dynamic linking, to pretty much every single runtime that we use today also in containers. Java, blah, blah, they're all dynamically linked. The linker, which is LD in most Linux distributions, is effectively doing this at runtime. You launch the program has been compiled to look for a linker. The linker goes and looks up the currently available dynamic libraries, scanning a series of paths, and then it adds whatever you add to the LD preload environment variable. So you create a list of libraries that will be looked at for things to plug in. The last library to the list wins. So the libraries are scanned kind of backwards, not really as forwards, but they get overwritten over time. And the most recent library wins. So I can actually override facilities provided by other libraries with LD preload. And then your program continues merrily doing whatever it is supposed to do. So, what are we trying to achieve with all these kind of arcane things? Well, we want to do this, but in a way that is independent from the runtime. We want to be able to set one environment variable and have it work whatever it is inside your containers. And there is actually more to this. It's not just about setting one environment variable, because there is a dynamic aspect, and we're going to talk about it later. So the idea is we're going to have a super generic way, without needing any annotations of any sort, to just get our tracers, metrics, and logs collection working out of the box. And this works by means of ELF. And I don't remember what ELF stands for. It's something linking, I don't know. It's effectively a metadata that exists in your files, your executables, to tell the linker what they need. And in this case, this is a dump of some of the ELF symbols of a Java virtual machine. There is a very interesting function. It's called getEnv, which stands for Get Environment Variable. Applications, not only Java, not only Node.js, they actually use the getEnv function provided by libc to look up environment variables, including Java _tools _options, Node _options, etc., etc., etc. So if we hijack getEnv, we get to return whatever we want, including the activation of our OpenTelemetry instrumentation. So this is actually a listing. You're not supposed to be able to read it. You just are supposed to be impressed by how ugly my C is. It's a very simple injector that is hijacking getEnv to actually always return the OpenTelemetry Java agent as something that the JVM should load. This is actually what we're using in production today in the Dash0 operator. We have a better version that I'm going to talk about soon. It works. It injects Java well. It also injects Node.js. It has a few drawbacks. It doesn't do input-output for reasons that I'm going to talk about soon, so there is no debug. There is also no validation that the files that I'm asking the JVM to load with the OpenTelemetry Java agent are actually there. And if you tell the JVM to load an agent that doesn't exist, the JVM explodes. So it's not nice. And there is a whole bunch of more things you can do automatically in injection. Okay, talk to me later about it if you're interested. So we have spoken about a lot of stuff. How does it feel in practice? Let's hope everything works. What you see on the top left is a simple pod specification that I'm using in the demo. Under it is the Docker file. This is a simple .NET application. Notice here Alpine. We'll come back to it later. And I'm going to deploy it. So in Kernel, I see my pod coming online. Let's have a look at it, the specification. There is a lot more stuff that was not in the YAML. This is expected. This is the admission controller mutating webhook doing its job. And let's see if it's doing something interesting. Yes, look at it. It's spitting out OpenTelemetry metrics, although there is nothing of OpenTelemetry in the original container image. This is the moment in which you give me a standing ovation. No, I get it. It felt so simple. Cool, so what? Is that all there is to it? Of course not, otherwise it wouldn't be a 30-minute talk. Let's go back for a second about what happens if you need to do the OpenTelemetry operator way, which is not what I use. I use the Dash0 one, but the technology, we want to contribute it upstream to the project. You actually need to pick the correct annotation for hotel.net auto runtime. Of the things that you see on the bottom, you just need one. And if you don't get the right one, it explodes. And this is where stuff gets interesting. Now, if you look here, we mentioned two things, Linux x64 and Linux Muscle x64. Raise your hands if you know what Muscle is. Good. Muscle is one of the flavors of libc. So your C programs tend not to be standalone. I mean, unless you really enjoy doing C, you don't invoke directly kernel APIs. You have the libc, the C library, to actually give you higher level functions like getenv, but there are also fopen to get files and stuff like that. And there are two flavors of this in the wild that we need to care about in containers. There is the GNU libc, also known as glibc, which is used by pretty much everybody, every Debian derivative, like Ubuntu, Mint, whatever, RHEL and its derivatives, CentOS, pretty much everything else, and then there is Alpine Linux with Muscle C, which is a very cool version of a libc, but it's different. And you could ask yourself, what happens if my application is compiled against the Muscle libc, and for example, I add to it a dynamic library that expects the GNU libc? This happens. This is Michael Bay, the movie director, and he likes stuff that explodes, and he approves of mixing libcs. So, takeaway. Your injectors should not link any libc, otherwise somebody's going to get hurt real bad. But what if what you inject depends on libc? Literally, the Java virtual machine, .NET, they all depend on libc. That's why they have the getenv function. So stuff can explode there as well. Case in point, in the OpenTelemetry operator, which is a really nice piece of machinery, you need to specify that it's going to use Muscle if your container does. By default, it will inject the build of the .NET profiler, which is not production profiling, is like the way a tracer and instrumentation is called in .NET. It will inject the one for libc, GNU libc, but if you have the wrong one, remember, it explodes. So we actually need to be able to figure out which libc flavor our application expects. And just one case in point, these things are on the pod. What do you think happens when you have multiple containers in a pod? Yes, either they explode or they all get the same if you get lucky, right? So we need to figure out which version of the libc to inject for. And this is where ELF comes back to help us, because not only in the ELF metadata of your application you see which function it depends on, but also which libraries it is supposed to link to. And this is where I had a love affair with Zig. It's a very cool language which provides a kind of high-level API similar to Go, but its standard library does not depend on libc. So I've been building an injector that built in Zig that can read the ELF metadata of the application it runs into. And by knowing which ELF metadata, I know which version of .NET to inject. And that's why the demo actually worked. Otherwise, boom. Is that enough? No, there is more work to do. You actually need to implement a bunch of different APIs to really cover all the possible use cases, like applications, updating the environment. So there is a little more work to do there. But in reality, the moment you implement those functions, which are relatively pretty simple, you get to an injector that does everything pretty correct. There can be some incompatibilities with some security tools that depend on LD preload, but actually as an industry, security has moved to eBPF, so we're good. And well, surprisingly, we made it. I actually expected this would take much longer. The takeaways are LD preload is amazing. It's going to help you a lot getting your applications instrumented fast, and hopefully it's coming to an OpenTelemetry operator near you. My name is Michele Mancioppi. If you have questions, I'll take them now. Let me know how I did, especially if I did not do great. And if you are a product person, as in product manager, with a taste for very technical observability stuff, and you're looking for your next gig, come talk to me at the Dash0 booth. Do you have questions? You do. So, which questions do you have? Yes? 1 minute, come on. Get one in that works. No? Very shy? Oh.
Okay, so I do know that LD preload does not work if I'm encountered with set UID or set capability binaries. I don't know, does it work if I specify a security context and drop all privileges?
Yes, because it has nothing to do with any privileges. eBPF needs security privileges, but LD preload is just a mechanism that is happening in the code of your application that is compiled. The moment that the files are in the pod and they can be read by your Java runtime, it will work. It will run inside your JVM process, and it will operate with the same permissions as your JVM process. You need absolutely nothing additional in terms of security privileges for your applications, which is one of the reasons why I love LD preload so much, because it works also in highly regulated environments.
Thank you.
Cheers. Good. I hope you liked it, and I'll see you around, I guess.